in a general CFT. So my talk has basically two parts. In the first part, I will be talking on Lightcone Bootstrap. Some of you have already familiar with this thing from my talk before, or some of my collaborators' talks before. And in the second part of my talk, we'll have the new approach to Bootstrap, which is from Mellin space, which will comprise some parts of Ananda's talk that we heard on Monday. So let me proceed. So yeah, part one, Lightcone Bootstrap. So I'll go through some very basics of CFT for the convenience of the audience. So consider two operators in a CFT, two scalar operators, phi and phi. Their product can be expanded as a sum over all other operators in the CFT. And if we use this OP, this operator product expansion in a 4-point function, we get another summation, which looks like this. So here, what we have done is we have expanded these two scalars and these two scalars differently, and then used conformal symmetries to rewrite the sum in this way, where in this sum delta phi is the conformal dimension of the operator phi, and these u's and v's are the conformal cross ratios, and this g is known as the conformal block, and c is the OP coefficient. So the expansion in this particular channel, which is called the S channel. So in this channel, what I had done is I had expanded these two and these two fields. I also could have expanded the first and fourth and second and third scalars separately, and then I would have got the T channel, which looks like this. And the Bootstrap proposal is basically nothing but these two different expansions should be equal. And this gives me the Bootstrap equation, or the crossing symmetry equation. And just to remind you, in this expansion, I have written the sum as I have labeled my operators in the sum in terms of the dimension delta and the spin L. So just let me write down a few things. And these are the cross ratios, and I have the dimension delta L, the spin I call L, and there's another quantity I'm going to refer to, which is called the twist, which is delta minus L tau. So take a free theory, or a mean field theory, or a free theory in ADS. Here what we have is, so the 4-point function of the scalars is just the weak contraction and has only these 3 terms. And on the right-hand side, I have written the T-channel expansion of the same 4-point function. And I have set the limits of cross ratios to be u much less than v much less than 1. This limit is called the Lightcone limit. And I could do this because I was free to choose any values of u and v if they are between 0 and 1. In this limit, the first term, e to the power minus delta phi, is a leading term, which is basically nothing but the identity operator of the OP. And the T channel, I have double trace operators which have this form, whose dimensions have this form, and in free theory, their OP coefficients are also known. So this C2 delta phi plus 2n plus 2l I plus l that I've written here, they're exactly known for free theory. And the good thing is, if I sum over all these things, they will exactly reproduce the leading term, which is e to the power minus delta phi. So this is how Bootstrap is satisfied for a free theory. And yeah, so the picture sort of looks like this. So on the left-hand side, I have this identity of exchange, and on the right-hand side, I have an infinite sum over double trace operators, and the sum of to give me the left-hand side. Now take a general CFT. So I have written the Bootstrap equation. This is the S channel, this is the T channel. And I have again taken the Lightcone limit, and once again I have the first term, the identity operator as the leading term. And the claim is, even in a general CFT, double trace operators should exist, and they are going to reproduce the leading term eq1 minus delta phi on the right hand side. So basically, so the claim means that double trace operators at large spin. So what it boils down to is this: that double trace operators at large spin must have dimensions which approach this value. And after I sum over these operators in the T channel, I will get the leading term. And so thus I get a very somewhat of a strong statement that the conformal blocks on the right hand side for large spin will look exactly just what they are for the free theory. So let me write down the dimensions of double trace operators. So what we get to learn is, in a general CFT, we will have double trace operators whose dimensions will approach 2 delta phi plus 2n plus l with increasing L, and plus I will have two corrections to them. So these corrections I call the anomalous dimension. This is a correction to the conformal dimension, and the OP coefficient correction, delta C. And another thing I know is these things should fall with increasing L, because after all I had to sum over all spins, and since the major contribution should be coming from the large spin, it implies that for increasing L, as I increase my spin, the dimensions should approach the free theory. So I can, from that, we can guess that the anomalous dimension of P coefficient corrections should fall with the spin. Now the subleading, so the previous, so till here I only looked at the leading term. Now let's look at the subleading term, which is this part. Yeah. Oh, because I claim that the operators, the operators, which double trace operators, should approach their dimension should approach 2 delta phi plus 2n plus l, and OP coefficient should also approach their free theory values. So, but they're not exactly at their free theory values. That's why there are these corrections. So then by anomalous dimensions, I mean the difference between the free theory values and the real one. So the subleading term, which I have written in terms of, so the subleading term comes from a minimal non-zero twist operator. So by minimal non-zero twist, I mean that the identity operator had that zero twist, and the next minimum twist that I have in the OPE will correspond to the subleading term in the Lightcone limit. So it has a twist tau m and a spin lm, and usually it's the stress tensor, which has the twist 2 and spin 2, and a small OP coefficient. And on the right hand side, I have these double trace operators, whose and I want to sum over all of these things to reproduce the subleading term on the left hand side. So how do I do that? So I take the log terms from the S channel. So this is the conformal block of the S channel. And if I take the log term somewhat looks like this schematically. And on the right hand side, I will again get a log term, but this log term will have the anomalous dimensions of the double trace operators in it. And to match these two, I get this anomalous dimension. How do I do that? So in this sum, this right hand side, there is sum over L, and this sum over L, since I am summing over the infinite number of operators, this sum over L I approximate as an integral over L, and this integral is satisfied only if this integral becomes this thing only if the gamma has precisely this form. So this gives me the anomalous dimension. I can do a similar analysis for the non-log terms. The non-log terms. So the non-log terms on the left-hand side looks like this, and the non-log terms on the right-hand side looks like this. And in this non-log term on the right-hand side, the OP coefficient corrections come in, and this allows me to calculate the OP coefficient in a similar way, and this comes out to have this form. The main results from the Lightcone Bootstrap are here. So let me write this down. And in pictures, it looks somewhat like this. That in the left-hand side, there is the identity exchange, and the subleading term comes from some stress tensor exchange or a minimal non-zero twist operator. And on the right-hand side, I have this sum over infinite number of operators. And hence, in this way, the bootstrap equation is satisfied. So, any question or comments from this? Yeah. So those things actually do come in for, so I have assumed that my theory is strongly coupled, which means this operator here is separated from all other operators in theory by some finite twist cap. And that's why all other operators are actually more subleading at large spin and in the Lightcone limit. But for weakly coupled theories, they do come in, and I really will have to sum over many operators here to match things. So part 2, which is the bootstrap so this is the new approach to bootstrap that we are working on. And so what we have here is, so this is the Mellin transform of a 4-point function. So has this form where this guy here is a 4-point function, and it's Mellin. This M here is the Mellin amplitude. So the Mellin formalism. So we have had many papers on Mellin formalism in the last few years, and anyway, and so the Mellin amplitude for a generic 4-point function with an exchange of delta and exchange of spin L and dimension delta has this form where this small m's are given by these things. So what we have here is So you see this, there is an integral over nu. Please don't confuse this v and this nu. There is an integral over nu here, and this thing, this m nu and m minus nu, this thing I might call the spectral function, just for convenience. In this Mellin amplitude, this C delta L that appears are the OP coefficients, and this P that appears are called the Mach polynomials. And so this M, the full thing will have poles exactly at exactly at the dimensions of the operators that are going to appear in the OPE. So what this means is, if I carry out this integral, I am going to reproduce the OPE at exactly the operators which corresponding to nu equal to delta minus h. Or yeah, but there are also some other extra poles in this thing. These extra poles come from these other gamma functions. So let's focus on the poles that come from this gamma square delta phi minus s. This s pole are going to give me some terms that are not present in the OPE. These things are what I call the unphysical terms. And the residues of these poles schematically are given by, I have written them like this. I'm going to mention what these Qs are in a moment. The Qs are given by this guy, where the M's refer to the spectral function that I just mentioned, that I showed in my previous slide. And the Qs, the capital Qs, are related to the Mach polynomials in this way. So the proposal is, make the M here, the Mellin amplitude, manifestly crossing symmetric. That is, write it as a sum of the M that is there in the S channel plus the M that appears in the T channel plus the M that appears in the U channel. Now, nice thing that we heard in Anando's talk is that the capital Qs here, they are orthogonal polynomials, which and from this, and using the orthogonality property of this QL, I have written the M's in the other channels, T and U channels, in terms of, I expanded these M's in terms of the capital Qs. And if I do that, the small Qs look like this. They are given, so they are given by the sum over all the operators that can appear in the OPE times d nu and dt, which is the Mellin variable, and over this spectral function. And using some properties of the Qs, I can actually one can actually see that these Qs are the Qt that I have here is basically equal to the Qu, which is the Q of the U channel. And so basically this is the so now that we have listed down all the unphysical terms like Qs, Qt, and Qu, what the next step is to sum them up and equate them to 0. That's what I've done here. So the Qs, Q plus Qt plus Qu, when I sum them to 0, this equation gives me the anomalous dimension. And if I write the sum, if I equate the derivatives to 0, then that gives me the OP coefficients. So why are there are two equations? Because these things are proportional to the log terms that comes from non-physical terms, and these things are proportional to the non-log terms. Okay, so here this is the expression for Qt in the T channel, and let's see what these capital Qs are, because I need them to compute this whole thing. The capital Q has this form in terms of a 3f2 hypergeometric function, and under a large L under the large L approximation, it reduces to a very nice simple form of some gamma functions. And using this form of Qt at large L, one can actually do this integral very easily. What you get is, so if you use this form, you see that at large L, there are only two poles of, both the integrals t and nu are going to have only one pole each. And if we use that, we get this simple form of Qt, which is just this. And the L dependent part, these L's are the operator of the T channel, and these L primes and delta primes are the operators that appear in the T channel. And now, so even in this simple form, I see that there is a sum over an infinite number of spins and infinite number of operators. So next step is, I assume that in the T channel there is a minimal twist operator present, just like what I had in Lightcone Bootstrap. So this minimal twist operator, I label it as tau prime equal to tau m, which is a twist, and the L prime and equal to Lm. So what I done here is this whole sum has basically so only one operator in this sum is going to contribute at a leading order because of the large L that I have here. So this sum goes away, and I get this very simple form of Qt, where the L is suppressed over minus L minus tau m. This is the reason that since I have L to the power minus L minus tau m, the other higher twist operators won't be showing up in this channel, in the T channel or the U channel. So now that I have a cute looking expression for Qt, so let's look at the S channel. The S channel, Qs, symmetrically it has this form. So what's the importance of this thing is that if we assume that the T channel is absent, there is no minimal twist operator in the T channel, this thing can be 0, which should be 0 if this term is absent. It can be 0 only if the delta has this value. So what it means is I have obtained the form of double trace operators only by just looking at this form of QS that appears in the TS channel. Oh, I think I might have missed a power, missed a inverse sign here. Yeah. So in presence of a minimal twist operator, what I will have is the dimension will get a correction, gamma, and QS will be proportional to this thing, the gamma. And if I use my expression QS plus QT plus QU, which is basically the new Bootstrap, the new Bootstrap conjecture that I'm using, I'll directly get this gamma equal to this thing, which is nothing but this exact same form that I got in the Lightcone Bootstrap. With a similar logic, I'm also going to get the OP coefficient corrections in the absence of a minimal twist operator in the T channel. I'm going to get the OP coefficients to be exactly equal to the known double trace OP coefficients, and with the minimal twist operator present, I'll get the OP coefficient corrections, which will again match with exactly what one gets from the Lightcone Bootstrap. Finally, I'm going to flash some new results for weakly coupled theories. So for using a double Lightcone limit, which is basically both U and V going to 0 at the same time, one gets the anomalous dimension for higher spin operators for a class of weakly coupled theories. This is work done by Alday and Zhiboedov. So what we have is the higher spin dimensions which have this form, the naive power quantum dimensions should look like this, and the anomalous dimension gamma L they are going to have this form. They are suppressed over an L to the power d minus 2, and there is a power series of log L's that are going to appear. All of them suppressed by a certain perturbative parameter G, where G is small parameter and delta phi, and this gamma phi is the anomalous dimension of the delta phi, the external field. In Mellin space, using an approach that I have just shown, one can actually determine the alphas that we have here. So these things were unknown previously, so one gets this exact same form, and this alpha i's, the alpha i's are actually now precisely determined in terms of the gamma phi's and the gamma 0. Then this gamma 0 is nothing but the phi square, the anomalous dimension of the phi square operator. So I'm just going to show flash results for phi to the power 4th theory d equal to 4 minus epsilon dimension as an example of what I've just shown. In d equal to 4 minus epsilon dimension, the anomalous dimension for these higher spin operators have this form, which exactly matches with the predictions. At large L, these things reduce to a simple form like this, and this behavior actually agrees with the predictions of Alday-Zhiboedov and also matches with the results of my previous slide. So I'd like to summarize my talk. So taking the Lightcone limit, one can obtain the anomalous dimension of weak coefficient corrections for the large spin operators in a strongly coupled theory, and we get exactly the same results for So last 2 points of my summary, we can get new results for large spin operators for a class of weakly coupled theories, and they exactly match with the known predictions. And just as Anindya mentioned, all these things can actually be repeated for our critical model, something that I'm doing with my advisor and Parijat, and I've skipped many details of my talk. For the YouTube viewers, they can click on Anindya's talk to get background details of whatever I mentioned. And yeah, and the thing I want to appeal to you is that the Lightcone Bootstrap took me 10 slides to come to this result, whereas after setting up my equations, I took like 4 slides to get to the same results and much stronger things for weakly coupled theories. And so,
what is the power law for
this log L is for weakly coupled theories, isn't it? For the weakly coupled theories, precisely for theories where there is no twist gap. So say the stress tensor is not separated from the other higher spin operators by some finite twist gap. So their dimensions, their twists are close by.